we present the on-keying data transmission achieved with Terahertz-to-Optical carrier conversion using an optical comb and Electro-Optic Polymer Modulator. Go to Introduction. One of the key components of Terahertz wireless communication for 6G is a Terahertz detectors. Conventional Terahertz detectors such as the Schottky barrier diode and the sub-harmonics mixer are based on the electronics. Unfortunately, these Terahertz detectors are complicated, fragile, and expensive for wide use of wireless communications. If the transmission information imposed on the Terahertz wireless carrier can be transferred to the optical carrier, photonic Terahertz detection can be achieved. It enables a seamless connection from a Terahertz wireless communication to optical communication, as well as the use of existing matured optical communication platform. To this end, the two key technologies are essential. The first key technology is the Terahertz to optical carrier conversion, like here, so from green to red color. In this study, we use the EO polymer modulator as a carrier converter. EO polymer or EOP has advantage of the higher EO coefficient, higher frequency response, and lower terahertz loss. The device structure shown here. The optical waveguide of EOP is sandwiched between the gold patch antenna for terahertz wave detection, like here. An optical carrier at 1.55 micrometer propagates this optical waveguide of EOP. Then, when a modulated terahertz carrier is applied for this device from the top, its electric field crosses the optical waveguide of EOP in which the optical carrier are propagated. As a result of EO pockets effect, a modulated optical sideband appears above and below the optical carrier. Importantly, so this modulated optical sideband is equivalent to the modulated terahertz carrier. By detecting these sideband with a photodiode, we can extract the terahertz modulation signal from the optical carrier. However, these optical sideband are quite weak, making it difficult to detect them in high SNR. For highly sensitive detection, we focus on the optical heterodyning signal enhancement. To achieve this, we have to further prepare another or second optical carrier close to this modulation sideband signal. So the second key technology is a dual wavelength optical carrier having a high stability and high OSNR. To this end, we use the optical frequency comb or OFC and optical injection locking or OEL. OFC is composed of a series of frequency spikes evenly spaced by a constant frequency like here. The most important feature of OFC is given by this simple equation, where the nu m is the optical frequency of OFC mode, FCO is a carrier envelope offset frequency, FREP is the frequency spacing, and M is a mode number of OFC. As FREP and FCO are photonic radio frequency signal around several tens megahertz, this equation indicates a coherent link of frequency between the optical and the electric region. Therefore, if both the FREP and FCO are phase locked to an electric frequency standard by laser control, uncertainty of the frequency standard can be transferred to nu m based on this equation. In this case, OFC can work as optical frequency ruler secured by the electric frequency standard. Next, we explain the OEL. In OEL, a stable but the low power master laser is injected into a high power slave laser cavity. As a result, the slave laser is passively phase locked to the master laser. In this case, we can combine the high accuracy of master laser and high power of slave laser. In our research, the OFC mode are used for the master laser, whereas the two DFB lasers are used for the slave laser. Each DFB laser at a different wavelength is locked to a corresponding different COM mode with a frequency separation close to the terahertz carrier frequency. This gives us a high OSNR dual wavelength optical carrier phase lock to the OFC. Next slide shows the experimental setup based on the two key technologies as explained earlier. We use Electro-Optic Modulator OFC or EOM OFC with a f-rep of 11 GHz and a center wavelength of 1.55 micrometer. From this OFC, we extract two modes that are separated by 10 f-rep or 110 GHz using optical bandpass filters. These two OFC modes, extracted two OFC modes, were used as a master laser and injected into the two DFB lasers, so DFB1 and DFB2. For the optical injection locking. As a result, we obtain the high OSNR dual wavelength optical carrier phase lock to the EOM OFC, consisting of a new one carrier and a new two carrier. The new one carrier was sent through the EOP modulator, which was irradiated with a terahertz wave. The terahertz wave was generated using a microwave synthesizer and frequency multiplier chain. The resulting terahertz frequency was 104 GHz and the power was 20 dBm. We tested both cases, so with and without the 2.97 GHz OK modulation or on-keying modulation. When the terahertz wave is applied, the new one carrier is modulated, and the sideband appear near it here. So the new two carrier bypass the EOP modulator and is later combined with the new one carrier and the new one sideband, like here. We set the optical frequency difference between the new one and the new two, so here and here, to be a 110 GHz and the terahertz wave frequency to be a 104 GHz. So the difference between terahertz optical separation, terahertz and the optical separation is 60 GHz. This means the new one sideband appears very close to new two carrier like here. So finally, we detect the optical bit signal between them using a photodiode and observe it as an RF baseband signal. We first evaluate the injection locking of DFB laser to EOM OFC mode. Left compares the optical spectra of injection locked DFB laser and extracted EOM OFC mode. The wavelengths are closely matched, indicating a successful OEL. Right shows a magnified optical spectra. Comparing these spectra, a 70 dB OSNR was what achieved. So this is 20 decibel better than without the OEL. In this way, the amplification and phase noise transfer of EOM OFC mode was achieved while eliminating the residual unwanted EOM OFC mode and ASE background. We next observe the new one carrier and its modulation sideband in OEL injection lock DFB1 laser when the terahertz wave is unmodulated. So here we use a single wavelength optical carrier. This compares optical spectra with and without irradiation terahertz wave. Without the realization of terahertz wave, only the optical carrier was observed. With the realization of terahertz wave, the neuron modulation sideband appear at 104 GHz away from neuron carrier. CSR bit carrier sideband ratio, or CSR, between the neuron carrier and the neuron sideband was achieved at 29 decibel, and the OSNR of neuron sideband was at 47 decibel. In this experiment, we use a single wavelength optical carrier. Next, we combine it with a second optical carrier close to the modulation sideband for optical heterodyne. Next slide shows the resulting RF spectra of the optical bit signal between the neuron sideband and the neuron carrier. So here. So when we applied a modulated terahertz wave, a spike-shaped signal appeared at the 6 GHz as expected from the frequency difference. Next, we apply a terahertz wave with on-keying modulation at the 2.97 GHz. In this case, we observe the broader spectrum around the 6 plus minus 2.97 GHz. So this kind of spectrum is typical of OK modulation and confirms that the modulation was successfully transferred to the RF baseband signal. Finally, so we observed the I pattern of a 2.97 GHz on-keying signal. On the left, you see the transmitted signal, so that the eye is clearly opened, and both Q factor and the bit error rate, or BER, indicates a high signal quality. On the right, you see the received signal after the terahertz-to-optical carrier conversion. The eye opening is slightly reduced, but it is still clearly opened. We measure the Q factor and the BER to be this value. These values are much better than the FEC limit, so both Q factor and the BER sufficiently exceed the FEC limit, confirming the error-free transmission. Finally, so we summarize the present talk using this slide. So EOP modulator generates a neuron sideband with a CSR of 38 decibel and OSNR of 40, maybe 49 decibel. And OEL achieves a 70 decibel OSNR optical carrier phase lock to the EOM-OLC mode. So terahertz-to-optical carrier conversion of 2.97 GHz OK signal using a dual wavelength optical carrier. The resulting Q factor was 77.2 and the BER was 3 by 10 power minus 13 beyond the FEC limit. And our future work is use of the 100 GHz spacing microcavity COM in place of the EO COM to reduce the influence of the phase noise. Thank you for your kind attention.